This is the solution video for question 19 from section B of the 4th sample test for CSAT. In this question, we're told there are N chemicals, and one of these chemicals, we don't know which, magically turns lead into gold in one day. We're told for our experiments, we may mix multiple chemicals with lead in one flask, and add one chemical to multiple flasks. So, given this, we're told we also have P flasks and a limited supply of anything we want, lead and each of the chemicals. And we're asked, what is the smallest number of days to ensure we find the magic chemical? The first thing to realise in the question is that we essentially have two cases, and one of them is quite easy. So the weird case, or the easy case, is P greater than or equal to N. So this means we can test every chemical in one day because we've got more flasks than chemicals. So we can literally just get every chemical, put a little bit of lead in, test it overnight, and then we'll know. So this is a very simple case. So we'll go for the case that is more difficult, P less than N. So let's have a look at this. So it's very hard to plunge straight into this. So let's do an example. So let's say P is 4, N is 10. So we'll have 4 flasks and 10 chemicals to begin with. And we'll try and work out how to do this for P equals 4, N equals 10, and then replicate our strategy for general P and N. So, firstly, we filled all 4 flasks with lead to begin with, because if we didn't have lead in one of the flasks, we're simply just not using it, because we can't achieve anything or get any meaningful results without adding lead. So essentially, we're going to choose to add some chemicals to each of these, and one of them or two of them, etc., are going to turn to gold. And if one of them turns to gold, we know the correct chemical must be from the set of chemicals we added. So it makes sense to use all the space we have. So it certainly makes sense to use all 4. And logically, the best strategy is to allocate them so the maximum of the number of chemicals in one of them is minimised. So we put chemical 1 in here, and we don't want to put chemical 2 in the same one, so we put 2 in here, 3, 4. Now we're forced to double up if we want to test 5, 6, 7 and 8. So we'll put 5 in here, 6 here, 7, 8. And then 9 and 10, we want to minimise the maximum number of chemicals in the flasks. So we put 9 in one of them, then put 10 in a different one here. So we have our setup now. So what does this mean for the next step? Well, essentially in the next step, we're going to get a replication of the same problem. We're going to know a set of some chemicals which might work, and we know the others don't. So we're based exactly where we started because we don't know anything more, and we're only interested in the chemicals where the flask we put them in had a reaction. So what's the worst case scenario here? Well, if one of these turns to gold, we'll have 3 left. If one of these turns to gold, we'll have 2 left. So this is the worst case scenario. So we'll have 3 chemicals to pick from in the next step. So I've written this. What does this mean? Well, this is called a ceiling function. So it's essentially do 10 over 4 and then round up to the nearest integer. So this essentially finds the worst case scenario for here. And we've written it like this instead of writing just 3, so we can generalise it a lot easier to N and P. So, for examples, how the ceiling function works, if we had ceiling of 3.2, we'd have 4, ceiling of 6.3 would have 7, and ceiling of 2 would be 2 because 2 is an integer. But in any case, we have ceiling of 10 over 4, which is 3. And now we do exactly the same with 3 chemicals. So we'd have ceiling of 3 over 4, but also we're sort of in this case now because we've got 3 chemicals to test and 4 flasks. And so after that day of testing, we'll be done. Because ceiling of 3 over 4 is 1. So we know exactly the chemical we want. So how many days does this take? Well, we've got 1 day to do our first set of tests and then a second day here. So we've got 2 days worth of tests for N is 10, P is 4. So we're happy pretty much that this is the best strategy for how we're going to do this. So we now need to generalise this to NP integers, assuming P is less than N, because we've already done the easy case. So, inspired by what we just did with p equals 4 and n equals 10, let's try and do it for general n and p. So we start with n, and then the best we can do after 1 day is have the ceiling of n over p. Then the day after, we'd have the ceiling of n over p, ceiling, and we carry on until we generated a 1 here, and then if we generated a 1 here, say, we'd have 2 days to identify a chemical. So we carry on until we got to 1. So, this isn't very workable. This is a horrible quantity to try and work out when we've done it 9 or 10 times. So what we hypothesise, and you'll be able to convince yourself of this, that essentially the gap between the ceiling of n over p and n over p, when we divide by p again, is so small that it doesn't change what the integer is above it. So we can actually argue that this is equivalent n to the ceiling of n over p to the ceiling of n over p squared to the ceiling of n over p cubed, etc. And you may be convinced by this, but at the end, after this question at the end, we'll formally prove it, just to address any worries if this is actually true. So where do we go from here? Well, we're looking for when the ceiling of n over p to d, because the d is how many days we've taken up to this point, is equal to 1. So that's when n over p to the d is just less than or equal to 1, and this we can rearrange quite nicely. So that's when natural log of n is less than or equal to natural log of d, natural log of p, d times natural log of p, by bringing the p to the d up and taking logs. And then we're almost done, because we know d is greater than or equal to natural log of n over natural log of p. We know we don't have to flip the sign at all, because natural log of p is positive, so that's fine, because p is greater than 1. And so we're looking for d, the smallest integer, when this is true, which is just given by taking the ceiling of this. So we know the number of days, d is ceiling of natural log of n over natural log of p. So this was the thing that we assumed earlier that we said we'd come back and prove. Now, you wouldn't have to prove this in the question, but it's nice to know it's true, and it takes a while to convince yourself it's true. So formal proof is nice to see. So we aim to show that the ceiling of n over p to the k, essentially if we take the ceiling over p, that is equal to the ceiling of n over p to the k plus 1. So, firstly, if p to the k is bigger than n, we're done, and this is fairly trivial, because this number will be less than 1, and this number will be 1 over p, so this is less than 1, so the ceiling of it will be equal to 1. So they'll both be 1 if this is the case, and so we're done. So let's suppose this isn't the case. So otherwise, we can write n is equal to q p to the k plus l, where q is some integer, and l is less than p to the k. And we're also going to assume l is not non-zero. Why is that? Well, if l is 0, then q over p to the k over p to the k ceiling is just q, and then over p to the k is just q, so both of these just come out as the ceiling of q over p, and so they are the same. So l not equal to 0 is the only case we really have to look at. So we've got this. Now, if we calculate n over p to the k ceiling, we have q plus l over p to the k ceiling, so q plus 1. And n over p to the k is q plus l over p to the k. Okay, so we've got our two quantities here, and we're going to argue by contradiction. So suppose for contradiction the conjecture fails here. Then what happens? Well, q plus l over p to the k over p, which isn't an integer because l is not 0, has to be less than or equal to some integer m, and that m has to be less than q plus 1 over p. This is the scenario that must happen for the ceilings of the two numbers not to be equal. There has to be literally an integer in between them. So we're looking at this over p less than or equal to m less than q plus 1 over p. Let's times everything through by p. So q plus l over p to the k is less than or equal to mp less than q plus 1. Now, you might be wondering where it's going, but the key is this, that we can write q is less than this because we know l is not 0. So what have we got now? Well, m's an integer and p's an integer, so mp is an integer. So what this line suggests is that between q and q plus 1, there's an integer that's not equal to either of them. Which makes no sense. There's no integer between two consecutive integers. So we've got a contradiction. So we have our claim as required.